In this video, I am going to talk about the inter-process communication in distributed operating system. And this chapter discusses about the issues, examples, and problems associated with the inter-process communication in distributed operating systems. The following topics are covered in this video. The fundamentals of communication systems, layered protocols, ATM networks, client-server model, blocking and non-blocking primitive, buffered primitives, unbuffered primitive, reliable primitives, unreliable primitive, message passing mechanism, remote procedure call. The single most important difference between a distributed system and a uniprocess system in the interprocess communication. In a uniprocess system, most interprocess communication implicitly assumes the existence of shared memory. A typical example is a producer-consumer problem in which one process writes into a shared buffer and another process reads from it. Even that most basic form of synchronization, the semaphore, requires that one word is shared. In a distributed system, there is no shared memory whatsoever, so the entire nature of interprocess communication must be completely has to be studied. The layered protocols. Due to the absence of shared memory, all communication in distributed system is based on message passing. When a process A wants to communicate with the process B, it first builds a message in its own address space. Then it executes a system call that causes the operating system to fetch the message and send it over the network B. Although this basic idea sounds simple enough, in order to prevent the chaos, A and B have to agree on the meaning of the bits being sent. If A sends a brilliant new novel written in French and encoded in IBM's EBCDIC character code, and B is expecting the inventory of a supermarket written in English and encoded in ASCII, communication will be less than optimal. Layered protocol is continued. To make it easier to deal with the numerous levels and issues involved in communication, the Internal Standard Organization has developed a reference model that clearly identifies the various levels involved. It gives some standard names and points out which level should do which job. The model is called the Open Systems Interconnection Reference Model, usually abbreviated as ISO OSI or sometimes just the OSI model. The OSI model, to start with the OSI model, it is designed to allow open system communicate. An open system is one that is prepared to communicate with any other open system by using standard rules that govern the format, contents, and meaning of the messages sent and received. These rules are formalized in what are called protocols. Basically, a protocol is an agreement between the communicating parties on how communication is to proceed. When a woman is introduced to a man, she may choose to stick out her hand. Open system interconnection model. In the OSI model, communication is divided up into 7 levels or 7 layers. Each layer deals with one specific aspect of the communication. In this way, the problem can be divided up into manageable pieces, each of which can be solved independent of the other. Each layer provides an interface to the one above it. The interface consists of a set of operations that together define the service the layer is prepared to offer its users. Connectionless versus connection-oriented. Similarly, to allow the group of computers to communicate over a network, they must all agree on the protocols to be used. The OSI model distinguishes between two general types of protocols. With the connection-oriented protocol, before exchanging data, the sender and receiver first explicitly establish a connection and possibly negotiate the protocol they are going to use. When they are done, they must release the connection. The telephone is a connection-oriented communication system. With the connectionless protocol, no setup in advance is needed. The sender just transmits the first message when it is ready. Dropping a letter in the mailbox is an example of a connectionless communication. With the computers, both connection-oriented and connectionless communication are common. The diagram shown on the screen defining the layers, interfaces, and protocols in the OSI reference model. In the OSI reference model, communication is divided up into 7 layers or 7 levels. Each layer deals with one specific aspect of communication. In this way, the problem can be divided up into manageable pieces, each of which can be solved independent of the others. Each layer provides an interface to the one above. The interface consists of a set of operations that together define the service the layer is operated to offer its user. In the OSI reference model, when process A on machine 1 wants to communicate with the process B on machine 2, it builds a message and passes a message to the application layer on its machine. This layer might be a library procedure, for example, but it could also be implemented in some other way. The application layer software then adds a header to the front of the message and passes the resulting message across the layer 6 or 7 interface to the presentation layer. The presentation layer, in turn, adds its own header and passes the result down to the session layer and so on. Some layers add not only a header to the front, but also a trailer to the end also. When it hits bottom, the physical layer actually transmits the message. When the message arrives at machine 2, it is passed upward with each layer stepping off and examining its own header. Finally, the message arrives at the receiver process B, which may reply to it using the reverse path. The information in layer N header is used for the layer N protocol. The physical layer just sending the bits. As long as no errors occurs, all is correct. However, real communication networks are subjected to error, so some mechanism is needed to detect and correct them. This mechanism is the main task of the data link layer. When it does is to group the bits into units, sometimes called frame, and see that each frame is correctly received. The data link layer does its work by putting a special bit pattern on the start and end of each frame to mark them, as well as computing a checksum by adding up all the bytes in the frame in certain way. The data link layer appends the checksum to the frame. When the frame arrives, the receiver recomputes the checksum from the data and compares the result to the checksum following the frame. If they agree, the frame is considered correct and is accepted. If they disagree, the receiver asks the sender to retransmit. Frames are assigned sequence number, so everyone can tell which is correct. In the figure shown on the screen, this is an example of A trying to send two messages, 0 and 1 to B. At time 0, data message 0 is sent, but when it arrives at time 1, noise on the transmission line has caused it to be damaged. So the checksum is wrong. B notices this and at time 2 asks for a retransmission using a control message. Unfortunately, at the same time, A is sending the data message 1. When A gets a request for retransmission, it resends 0. However, when B gets a message 1, instead of the requested message 0, it sends control message to A, complaining that it wants 0, not 1. When A says this message, it shrugs its shoulder and sends message 0 for the third time. OSI layers. OSI layer, it is given from the top, application layer, presentation layer, and session layer. The application layer is really just a collection of miscellaneous protocol for common activity, such as electronic mail, file transfer, and connecting remote terminals to computers over a network. The best known of these are the X.400 electronic mail protocol and X.500 directory server. The presentation layer, unlike the lower layers, which are concerned with getting the bits from the sender to the receiver reliably and efficiently, the presentation layer is concerned with the meaning of the bits. Most messages do not consist of random bit string, but more structured information such as people names, addresses, amounts of money, and so on. Next one is the session layer. The session layer is essentially an enhanced version of the transport layer. It provides dialog control to keep track of which party is currently talking, and it provides synchronization facilities. OSI layers continue. The transport layer. The packets can be lost on the way from the sender to the receiver. Although some applications can handle their own error recovery, others prefer a reliable connection. The job of the transport layer is to provide this service. The idea is that the session layer should be able to deliver a message to the transport layer with the expectation that it would be delivered without loss. The network layer. On a local area network, there's usually no need for the sender to locate the receiver. It just puts the message out on the network and receiver will take it up. A wide area network, however, consists of a large number of machines, each with some number of lines to other machines, rather like a large-scale map showing major cities and roads connecting them. For a message to get from the sender to the receiver, it may have to make a number of hops, at each one choosing an outgoing line to use. The question of how to choose the best path is called routing and is the primary task of the network layer. Next one, data link layer. The physical layer just sending the bits. As long as no errors occur, all is correct. However, real communication networks are subject to error. So some mechanism is needed to detect and correct them. This mechanism is the main task of the data link layer. What it does is to group the bits into units, sometimes called frames. Next is a physical layer. The physical layer is concerned with the transmitting the zeros and ones. How many volts to use for 0 and 1, how many bits per second can be sent, and whether transmission can take place in both directions simultaneously are key issues in the physical layer. In addition, the size and shape of the network connector as well as the number of pins and meaning of each are concerned in the physical layer itself. Lower level protocols completed. Transport layer. Lower level protocol, the physical layer, which is standardized electrical, mechanical, and signaling interfaces. Data link layer, it provides low level error checking, appending the start and stop bits to a frame, and computing the checksum values also. In networking, routing is done. IP packets need to be set up. Each packet in a message is routed independently of the others. Transport protocols. Transport layer, there's sender side receives message from higher layer, divided into packets and assigns a sequence number. Reliable transport can be built on top of connection or connectionless networks. Most common transport protocols are TCP/IP. Reliable and unreliable communication. Transmission control protocol guarantees reliable transmission if packets are lost or delayed. Packets must be acknowledged by the receiver. If acknowledgement not received in a certain time period, it will be resent. Reliable communication is considered connection oriented because it looks like communication is circuit switch network, one way to implement a virtual circuit. Other virtual circuit implementation at layers 2 and 3. Example, ATM, X.25, then frame delay. Reliable and unreliable communication. For application that value speed over the absolute correctness, TCP/IP provides a connectionless protocol called UDP. It's a Universal Datagram Protocol. Client server application may use TCP for reliability, but the overhead is greater. The alternative is that application provide reliability, the end-to-end argument. The higher level protocols are session layer. It is very rarely supported. It provides dialog control. The presentation layer, also not generally used, it cares about the meaning of the data. Application layer, originally meant to be a set of basic services, now holds applications and protocols that don't fit elsewhere. Then middleware protocols. The Tannenbaum, the communication network author proposes a model that distinguishes between application program, application specific protocol, and general purpose protocols. Compared to the OSI model, the session and presentation layer have been replaced by a single middleware layer that contains application independent protocol. These protocols do not belong in the lower layers. There are general purpose protocols which are not application specific and not transport protocols. Many can be classified as many middleware protocols.